I think this is the assignment from the first class.
No, sir. I submitted in the
Different
notes,
one.
so I think it didn't come.
Oh, acha, it has not been updated. Okay. So in the last lecture, we did tell delta H is equal to delta U plus delta NGRT. Okay. So let us do one more question. Let us do one more question like this, and then we can start with the rest of the things. Write a question. The heat of combustion of methane the heat of combustion of methane gas है ना CH4 at constant volume is measured to be minus 885.4 kilojoule per mole at 298 Kelvin. Calculate the value of enthalpy change. Okay, so write this down. Similar question, if you just look at the question that we did yesterday, the last question, it's NH2CN1. This similar to that. So look how we did that question, and then try this one also.
Sir?
Yeah, tell me.
Sir, usually will they give us the reaction in the question, or like we have to write it?
No, it is not क्या बोले हम आपको, not necessary. For example, in this reaction, if in this question they have not given you the reaction, right?
Yeah.
So it is not necessarily that they will be giving you reaction, but they will say something that combustion is happening here, right? So maybe you can deduct what is the reaction going on.
Okay, sir.
So combustion means reaction with oxygen, है ना? Then you write the balanced chemical equation. So that is the only thing that is different from the last question, that in this question we don't have the reaction given. Acha, I hope all of you would have got your examinations date. Yes or no?
Yes, sir.
Final
Yes, sir.
examination. Yes.
Yes,
Okay.
sir.
Fine. Can you? Okay, maybe I have asked you this earlier, but can you please send when are your examinations starting and ending, both the dates in the chat. Send in chat, okay? Start, end. Okay, yes, Majid, that is correct. Okay, Khalil and Memuna. March first week for Minashi. Okay, but still now they did not inform about them. But pre-boards are from 20th Feb. Okay, fine. And this first week of March. Khalil का सबसे पहले हो रहा. Khalil, is this like your examination? This is pre-board or something?
No, sir, this is final examination.
Final examinations. Okay. But everyone else they are having from the last week of Feb, I guess, or first week of March. Also, some of them. Okay. Yes, Khalil, correct. Correct. Oh my God. This is periodic test. This is periodic test, na? Minashi,
Yes, sir.
this is periodic test, na?
Which
I-
first
You only Mazia. Sorry, not Minashi. Mazia.
yes, sir.
अच्छा. हाँ. ये
No,
तो periodic test है.
they didn't give us final exam dates.
अच्छा. तो आपको 5 तारीख से एग्जाम चालू है. Oh my God. अच्छा, and one more thing, 5, 6, 7, 8, 9, 10. I think this is periodic test. This is not boards. Your syllabus is complete in your school, Mazia?
Yes, sir.
Syllabus is complete. Okay, then maybe it can be. Okay.
No, this is periodic test, but they didn't give us final exam dates.
Final exam date they have not given, you know. Okay,
No.
fine. It's periodic test only. Okay, fine. So for this question, we know that they are asking now which are the word important. Who will tell me what words? The combustion word is important here. What word is important? Tell me, guys. In this question, what other word is important?
Volume.
Yes, Razan, can you please speak loudly? Could not hear that.
Constant volume.
Very good, है ना? Constant volume, it is important. है ना? So these are the things that you have to pick out. Not only the values. Yes, Mazia, correct. No? Constant volume. So they have given us constant volume. That is the heat that is evolved at constant volume, which is QV, right? Which is QV, which will be equal to delta U, right? Delta U. And they're asking the enthalpy change, and they are saying what is the delta H. So we know that there is a relationship. Yes, Maimuna, correct. There is a relationship between delta H and delta U. So delta H is equal to delta U plus delta NGRT, है ना? But there's also one more formula, delta H is equal to delta U plus P delta V, है ना? But this is not something that you will be very often using. That is why you may forget it also. But please remember that this is also one of the formula. Maybe in some question you will be given the change in volume and the pressure. But at this point of time, so this formula is of no use because they have not given me pressure or something. Okay, so we will not use this formula. Now they are saying that delta NGRT, that means change in the number of moles of gas in a particular reaction. So we'll have to write the reaction, that is CH4 plus 2O2 gas is going to give me CO2 gas plus H2O, CO2 gas plus H2O. Now it is important, what will be H2O at 298 Kelvin? H2O at 298 Kelvin will be liquid, right? Yes or no, tell me. Now
Yes.
this will be 2H2O. This will be 2H2O. Okay. Now these are the like slight. So in thermodynamics, you have to have a very detailed look in the questions, right? So all of these matters. What is the state and the phase of system? This is also gas. So we can write delta Ng. It is equal to number of moles of gas in the product minus number of moles of gas in the reactant. So in the products we have how much? Only one, no? And minus 2 plus 1, 3. So this will be equal to how much? Minus 2. Right, guys? minus 2. Now you just need to put delta H. It is equal to delta U is given how much? 885.4 into 10 to the power 3 joules. Why joules? Because we have here the term R, and R should also have the same type of value. Now, both of these should have same units. Minus 2 into, because it was plus and minus 2 will be 2 into, R is 8.314 into temperature is 298 Kelvin. So if you calculate this, you will get approximately 890.35 or something kilojoules. Okay, so write this down. 0.5 you guys are getting, so it may be 0.5 then. So somewhere around 890 kilojoules you will be getting the answer. Okay, I'm moving. So let me know if you have not done. Okay, let me know if you have not done. Right. Again, so you will be just writing the questions and no need to write whatever topics I'm writing here. Okay, so the notes kind of thing. Now we know that delta H has two relationships. Delta H and delta U, it has two relationships. One of them is delta H is equal to delta U plus delta NGRT, and the other one is delta H is equal to delta U plus P delta V. Now, if I say that there is a reaction which is done in a closed vessel, okay, so reaction in a closed vessel, right? Reaction in a closed vessel where delta V is equal to 0. Delta V is equal to 0. In that case, what I can write? I can write that delta H will be equal to delta U. Delta H will be equal to delta U because delta V is 0. So 0 into P will be 0 and delta H is equal to delta U. Okay, now please listen, don't write anything. Now, a reaction that doesn't involve gases. That is, what does it mean? It means that the number of moles of reactants will be equal to number of moles of product, which will be equal to 0. Both of them, because the reaction, it does not involve any gases. It means number of moles of gases in reactant and number of moles of gases in product will be equal to 0. And if it is 0, then also we can write delta H will be equal to delta U. And the last point, so reaction in which number of moles of gases in reactant and product is same. That is, reactant it is equal to Ng product. So what will happen? Ngp minus Ngr will be equal to 0. If I subtract both of them, it will be equal to 0 because they have equal number of moles in the reactants and the product also. So we can, in this case also, write delta H will be equal to delta U. Okay, delta H will be equal to delta U. Okay. Next thing is that in the earlier questions, whatever we have learned till now, to calculate delta H or delta U, you at least needed one of them, either the delta H to calculate delta U, or delta to calculate delta U, you needed delta H, or to calculate delta H, you needed delta U, and a reaction that is happening. Now, how do we measure delta U? We have been given it was measured to be itna kilojoule, and in the previous reaction also, previous question also, we said that it is measured to be itna joule. So let us start with simple ideas. How can we prepare a device? How can we make a device which can give me what is the heat transfer, right? What is the heat transfer from system to surrounding or surrounding to system when a reaction is happening? Okay, so all of you please get the idea that there is a system. In this, some reaction is happening and there is some heat involved. Okay, there is some heat involved. There is some heat involved, and either the heat is coming from surrounding to system or the heat is going from system to surrounding. So we have to quantify this heat, right? We have to quantify this heat, and we will understand how to make a device, in order to quantify this kind of, heat transfer from system to surrounding, the exchange of heat from system to surrounding. All of you are okay till here? Tell me, guys. You have a clear idea what are we going to do now?
Yes, sir.
Okay, fine. So this is our system. Okay, this is our system, and this is our surrounding. This is our surrounding. Okay. Now, again, for practicality, you remember now, surrounding is what? Where we have where the system changes in system, it influences surrounding. So the volume around which the volume around which a particular system is making any changes in the surrounding, that will be the practical surrounding. So theoretically, surrounding is anything that is not system in the universe, that is surrounding. But for practical purposes, what is surrounding? That part of the universe which is affected by changes happening in the system. You understand? You remember this from the first lecture, guys? Yes or no?
Yes, sir.
Yes, na? So just imagine that what we are doing, we want to see how much a particular firecracker, how much heat does a firecracker evolve. So what I am doing, I'm burning the firecracker in Delhi, and I'm saying we will take the theoretical surrounding. So the surrounding is anywhere in the universe where there is any part of this universe which is not system is surrounding. So I went to Bahrain, and I'm seeing what is the heat involved. So that is not practical. That is, I mean, we cannot predict or we cannot measure anything in Bahrain if I'm burning firecracker in Delhi. So will have to limit the surrounding with respect to the system. Fine. So our surrounding will be something very limited. Okay. Now you tell me, if the system evolves heat, if the heat is evolved by the system, then what is going to happen? What change can I see? What change can I see in the surrounding? There are only few things that I can measure. Okay, there are few things I can measure. I can measure the pressure, I can measure the volume, I can measure the number of moles in the surrounding, I can measure the temperature in the surrounding. What else I can measure? Number of moles means I am measuring mass also. So these are the most important parameters in chemistry that you can measure. So now you tell me, what change will you see if the system is giving out heat to the surrounding?
The temperature increases.
Yeah, there will be an increase in temperature. Increase in temperature. Okay, fine. There will be increase in temperature. And if the surrounding is giving heat to the system, then what will be happening? There will be a decrease. This is the surrounding, and there will be a decrease in temperature. Yes or no? Yes or no, guys? Tell me.
Yes, sir.
Okay, fine. So now we will be inferring about the heat. We will be inferring and we will be measuring heat by the help of temperature change. Okay, by the help of temperature change. Okay, now you tell me, I'm giving you two cases. This is simple system and this is our surrounding. Okay, so I have made the surrounding small here, and then we have the same system. Okay, the same system, and there is a large surrounding. Okay, the last here we are having large surrounding. So, and same amount of heat is liberated by the system in this case also and in this case also. Fine. Now you tell me, where will I see a large change in temperature? There will be changes in temperature of the surrounding. In both the cases, the temperature will increase. But where will I see a large change? Think about it. Small one or the big one? The small one. All of you agree? All
Yes,
of you
sir.
agree? Yes or
Yes,
no?
yes.
There will be a small one. Okay. So one thing I can say that this system, this surrounding here, it is temperature sensitive, right? Because it is heat sensitive, I can say, yeah, heat sensitive, because even if I give small amount of heat, the increase in temperature will be very high. Yes or no?
Yes.
Okay. Now from this sensitivity, I can talk about the capacity of holding heat. Now, if something is if the temperature of a particular surrounding is increasing very rapidly, that means I can say that the heat capacity of this surrounding is not very much, right? It is not very much. For example, if I talk about the heat capacity, how much heat a particular thing can hold, and I talk about water. Okay, I talk about small amount of water and I talk about a large amount of water. Fine. Now, this particular water, it will require some Q heat to get evaporated. And at that point, I will say that the heat capacity is that much only, like the amount of heat I am giving to a particular water body till it gets evaporated. So if it is not getting evaporated easily, that means it has a higher heat capacity. And in this case, let us say that I am giving Q2. So we can easily say that Q2 will be greater than Q1. Yes or no? We can give more heat to the larger water body in order to evaporate rather than the smaller water body. Yes or no? Which will
Yes.
require, okay, fine. Now we understand that the capacity of holding heat for different systems is different. Okay. Now this particular topic of heat capacity, it is not there in your syllabus, but as you can see, it is very important in order to understand how are we going to measure the delta H's and delta U's of different reactions. Okay, different reactions. So let me just talk some few things about heat capacity, and then we can move on towards the device. Okay, then we can move on towards the device. So heat capacity. Heat capacity, it is given by C. Okay, it is given by C. Okay, and we can say that it has heat capacity. I can say that Q, if I give more amount of heat in a particular system, there will be a large change in temperature. There will be a large change in temperature, and Q is, there will be a proportionality sign which will depend on different systems. Like if I'm heating water or if I'm heating iron, the heat capacities of both the systems will be different, and that will be reflected in the temperature change also. That will be reflected on the temperature change also. And then I can say that it is equal to C into delta T, where C is the proportionality constant, and it also infers the heat capacity of a particular system, Now you can perfectly see that C will be equal to Q upon delta T, Q upon delta T. Now C is equal to Q upon delta T, and I can say also one more thing. Whenever we define a constant, what do? Let us take the delta T as 1. The increase or decrease in temperature is how much? The change in temperature is equal to 1. So C will be equal to how much? If delta T is equal to 1, C will be equal to Q, right? So heat capacity, if I talk about in terms of quantity, I can say heat capacity is the heat required by the system to increase the temperature by 1 degree, by 1 degree Celsius or 1 Kelvin, same thing. 1 degree Celsius or 1 Kelvin. Now, if the heat capacity is higher, that means high amount of heat will be required to make that 1 degree change, right? To make that 1 degree change. All of you understand this concept now about heat capacity? Yes or no?
Yes, sir.
Okay. Now, as we know, delta H and delta U, right? So one is at constant volume, one is at constant pressure. So for heat capacity also, we can write the heat capacity, or rather not write, but we can measure the heat capacity of a particular system in two different ways. That is, we can either have a condition in which there is constant volume, or we can have a system in which there is constant pressure. Okay. Also, we can also measure the heat capacity in terms of grams and in terms of moles also. So let me just first of all say that about. So we have heat capacity. So we can measure and we can store the data of different heat capacity in two ways. We can write about specific heat capacity. Specific heat capacity, and this depends on mass, like per gram. This depends on per gram. It is SHC. It is equal to the heat capacity of the system divided by how much mass of the system is there in terms of grams. So you can say that C is what? C is Q upon delta T, right, into mass. To mass in grams. This is SHC. Or else you can also calculate heat capacity in terms of moles. That will be molar heat capacity. Molar heat capacity. So this will be in terms of moles. Molar heat capacity is shown as Cm. This will be equal to C upon number of moles, right? Number of moles. So you can write this as Q upon delta T. For number of moles, we have the symbol N. We have the symbol N. Fine. Yes or no? Any problem till here? Guys? No, no. Okay. Just write a note. Heat capacity is extensive. And a heat capacity says that how much heat a particular body can hold. So a small water body will hold less amount of heat and a large water body will hold a very high amount of heat, right? So heat capacity is extensive. It will depend on the mass, but SHC, that is specific heat capacity, and Cm, that is molar heat capacity, are intensive properties. Why? Because when we standardize a particular thing by dividing it by mass, then it doesn't, it doesn't matter now. It doesn't matter now. Like if we are having small amount of water, then we are dividing by small amount of mass. If I have a large amount of water, then I'm dividing by large amount of mass also. So we are getting same values, and then we will be getting same values. And also the ratio of two extensive properties is intensive. But SHC and Cm, that is molar heat capacities, are intensive properties. Now, next thing is that for measuring of the delta H and delta U, I need to get two types of heat capacity. The one which is measured at constant volume, and the other is measured at constant pressure. Okay, so we can again write heat capacity. Okay, so the previous one was in terms of how are we writing and how are we representing the heat capacity, and the second classification that I'm doing here, it is how are we measuring the heat capacity. So either it can be measured at constant volume or it can be measured at constant pressure, and both are useful. So at constant, volume will be constant, and if the volume is constant, we will call that heat capacity, which is represented by C, we'll call that as CV. And where the pressure is constant, we are going to call it CP. And please remember what is the use CPCV, because we have to, please remember that we have to measure the delta H's and delta V, delta H's and delta U's. Now, in this case, that's CV, right? CV. So we can write, what is the expression? The expression is Q, it is equal to C delta T, right? Then QV will be equal to CV delta T, the heat capacity measured at constant volume. Similarly here, we know that Q, it is equal to C delta T. Now at constant pressure, QP will be equal to CP delta T. Yes or no? Now you can see that this will be also equal to the delta U, and this will be also equal to delta H, right? So we are measuring in those two terms just to measure the delta H's and delta U's. Fine? Fine, guys, yes or no? Any problem, guys? Till here?
No, sir.
No, na? No. See, now we are going to make a device. Now we are going to make a device in which once we will keep the constant volume, and in one of them we will keep the pressure constant. Okay, volume constant and pressure constant. Now we need two things, you know. So we have these two parts. If we can measure the heat capacity and the change in temperature, then we are measuring delta U and delta H. And how are we configuring a particular device? That will depend on whether we are measuring the CV or whether we are measuring the CP. We are measuring the CP or we are measuring the CV. So for constant volume, so before constant volume, let us start with constant. Yeah, let us start with constant pressure. Okay, let us start with constant pressure. So if I start with constant pressure, now my idea is I will keep a system like this. Okay, I will keep a system like this. There is some reaction happening in the system, and I will surround this system by water. Okay, by water rather than surrounding with some solid substance. It is good to surround it with some liquid substance, and water is the most available liquid, and also much of the properties and the data for water is very easily available. If I surround this with water, and I will put a thermometer here, right? So this is my thermometer, and it is going to tell me the temperature. It is going to tell me the temperature. Okay, that's it. Now one more thing I can add is a stirrer, because let us suppose that the system is giving out heat. The system will be giving out heat like this, right? So this stirrer will, what it will do, it will homogenize the temperature increase. It will homogenize the temperature increase. Otherwise, you will have like kind of slightly different temperatures at different point of water. So a stirrer will just homogenize the temperature all over the water body. Now, when we see, we will get the, what do we need? Here we have the thermometer. It is going to give me the delta T, and then the CP, right? CP of water, right? CP of water rather than not CP of water, but I can say that the CP of this device, CP of this device, because this box here, it will have some heat capacity. This thermometer, it will have some heat, right? This stirrer will also have some heat capacity. So overall, the CP of this whole system or this whole device, the CP of this whole device, okay, that is given by the manufacturer. That is given by the manufacturer. What you need to do, you need to put a reaction inside the device and just measure the temperature change. Just measure the temperature change, and then what you will get CP into delta T, right? And you are measuring delta H. You are measuring delta H. Easy? Yes or no, guys? Tell me. Any problem?
No, sir.
No, na? No? Okay, fine. This simple device, it is known as the coffee cup calorimeter. This is known as coffee cup calorimeter. Okay, or simple calorimeter, you can say. Simple calorimeter. Okay. Next is the, when we are measuring, when we measure delta U, okay. So for delta U, you need to have a constant volume. So the device is slightly more, what I can say, a bit complex. So just let me pull up the photo. Bomb. Okay, so this bomb calorimeter, it is mostly used, well, not mostly, it is only used for combustion reactions. Okay, it is only used for combustion reactions. This is bomb calorimeter. I will tell what is happening here, but the main concept is the same, that how we started now. Whatever system is giving out heat, we can measure that in terms of temperature. Now we needed to standardize something that will measure the heat capacity of the system. The same idea is the same. The working of this bomb calorimeter is a bit detailed, nothing else. Bomb calorimeter. bomb calorimeter. Okay. Now in this case, you can also identify a few things that is similar to the simple calorimeter. So in thermometer, it will measure the delta T. Okay. Now we have a stirrer to homogenize the heat, right? To homogenize the temperature change. And in sample, you will be burning something. Now there is a bomb here. We will tell what is bomb. What is the use of water? Water is a medium. Water is acting as the surrounding, and water is acting as the surrounding of whatever changes is happening inside the system. Okay. Now in this, what happens? We have some firing leads. We have some oxygen inlet, and there is a sample here. Okay, this sample here. So this sample, when you input oxygen, the pressure is going to change, but the volume is not changing because it is thick. Okay, nothing can happen. Nothing can happen. The volume is not going to increase. Now, here we have firing leads. That means you will burn this down. So as you have firecracker and the latti hota na, what do you say? You say latti. I don't know what is the English word for that. You have a thread. You have some thread. If this is a bomb, so this thread now, this is firing lead. So here you burn and then it goes down. So those firing leads are there. Wait a second, I need to reshare this thing. So firing lead will increase the temperature, and if something gets appropriate temperature, it will react with oxygen to give combustion reaction, right? So this whole thing burns, and then you get an increase in temperature, and that will be represented by the delta T. And for water, we will take here CV, right? Because it is constant volume. CV of water. Not water, again, I am saying not water, but of device, complete device. Hai na? Complete device, that is the bomb calorimeter. And delta T you will be seeing in the thermometer only. And you just multiply these two things, CV into delta T, you will be getting delta E. Hai na? You will be getting delta E, change in internal energy. Now, this is how you've seen a calories. In food labels, you must be seeing calories. So all the calories are measured in this way only. So they put some amount of food inside the bomb calorimeter. They fire the leads. They measure the temperature change. They get the CV of the device, that is the bomb calorimeter, from the manufacturer. And then you get the delta U, which will give you the calories, because it is in terms of energy only. Okay. So this is how you measure the calories. But can you see anything that is, what I can say, what is the limitation of measuring calories in this way and then using it for dietary prescription? I would say, if you want to make a diet and that diet should be calorie restricted or something, so the way we are measuring calories and how our body, it consumes a food and how it derives energy, that is going to be a bit different from the bomb calorimeter, right? Because our body does not just burns, there are many things involved. Yes or no?
Yes, sir.
So when you have calories that is written in a food label, so they don't represent the actual calories you are getting. They represent somewhat higher calories only, not lower, but always somewhat higher calories. Okay. So this is all about bomb calorimeter. Now let us do a question, because at the end you will have to do the question. I hope you all understood. Whenever you're revising this chapter or something, please start with a simple notion that you have a system. You want to measure the delta H and delta E. So heat is transferred like this. What will happen? What is the consequence? The temperature will increase. So delta T. So these are the two things that you have to measure. So this delta Q, that is the CV into delta T. CV into delta T. Okay. Write a question. It 1.25 gram of octane. Formula for octane is C8H8 is burnt. (1.25 gram of octane is burnt in excess of oxygen in a bomb calorimeter. in a bomb calorimeter. The temperature change was measured to be, the delta T was measured to be, was from 294 Kelvin to 301 Kelvin. Okay, this was the temperature change. And they have given if the heat capacity of bomb calorimeter and its contents is 8.93 kilojoule per mole. Then calculate the heat transferred to the calorimeter. Okay, so this is a very simple question. In this question, what they are asking, the heat transferred to the calorimeter. So you have a system, right? And here we have the bomb calorimeter. You have to measure the Q. You have to measure how much heat is transferred. Now this Q, it will be equal to CV into T into delta T, right? What is the CV? They have given the CV as 8.93 kilojoule only. We can take kilojoule. Okay, 8.93 kilojoule per mole. Okay, into the delta T is how much? 7, right? Wait a second. This will be not kilojoule per mole. I'm sorry, this will be kilojoule per Kelvin.
Sir, in the brackets, it should be C8H18, right?
Yes, I'm sorry. H18, correct. Okay, but you will see that this information is not useful for us because it doesn't matter. It doesn't matter what thing we are burning. What matters is the delta T. What matters is the delta T, how much change is happening. So that is how we are measuring the heat. Okay, so but yeah, it should be 18. 8.93 and delta T will be equal to 7 kelvins, right? You can just change per mole, not per mole. This is kilojoule per Kelvin. So this Kelvin and Kelvin inverse will cancel each other out, and you will get the answer as 8.93 into 7 kilojoule. This is how this is the Q, and this is also the delta U. Okay, this is also the delta U. Now, since this delta U is given, we can calculate the delta H. For calculating the delta H, we need what is the reaction. So in that case, we are needing this one, 1.25 into octane. Okay. So write this down. Let me know if you're done. Calculate the delta U. Calculate the delta U. 9 is 60. It will be approximately 63. Yes, Razan, I think that is correct. Yes, Khalil, yeah, correct. 62.9. Done, all of you?
Yes, sir.
Okay, fine.
Yes, sir.
Now, when we got a device where we can measure the delta H, right, where we can measure the delta H of a particular reaction, and any reaction that is happening, we can measure the delta H of that reaction. Now, scientists, they standardize some delta H's. They standardize some delta H's and they stored their values for further use. For example, if they, let us say, reaction of CH4 plus O2 gives me CO2 plus H2O. And this is not balanced, but let us see, this is the reaction, burning of methane. So burning of methane at a particular temperature and a particular pressure, they calculated the value and they said that that is the enthalpy of this reaction. This is the enthalpy of this reaction. And then they set up a standard. They set up a standard. It means, standard means they measured the delta H of many reactions, delta H of many reactions at some condition, and those condition was at 1 bar pressure. Okay, at 1 bar pressure. So at 1 bar pressure, they measured the delta H, because we know that delta H, what should be constant? Pressure is constant, na? Pressure is constant. So they measured the delta H at 1 bar pressure for many reaction, and they called that this is the delta H naught of the reaction. This is the delta H naught of the reaction. So whatever reaction that you are going to learn, they all will have some delta H naught that is already measured. It is already measured and it is stored. Now we can use this delta HR for various other purposes. Okay, so first of all, we will start with thermochemical equations, because when you write a chemical equation like this, so we balance it. CH4 plus 2O2 is going to give me CO2 plus 2H2O, right? And if I just add the information of delta H now, the thermochemical equation, it will become a thermochemical equation, which also has the information of the heat change during the reaction. Okay, so a chemical reaction which also has the information of the heat change during reaction, it is known as thermochemical equation, a balanced chemical equation. So this whole thing is the thermochemical equation. Okay, so let me just write the topic. You guys don't write. Thermochemical equation, thermochemical equation. So balanced, this will be a balanced chemical equation which gives the heat change during reaction. Okay, this is the balanced chemical. For example, carbon, which is solid, plus O2 gas gives me CO2, and delta H for this reaction, it is equal to minus 393.5 kilojoule per mole. Okay, now this whole reaction, it can also be represented like this. Okay, carbon solid plus O2 gas, it is going to give me CO2 plus 393.5 kilojoule of heat. Now please remember, when I'm writing delta HR for this reaction, okay, delta HR for this reaction, then I'm writing minus 393, and when I'm writing it like this in side of products, then I'm writing plus 393. So this plus and minus, I hope you understand, this minus here, it means that it is happening in the product. The heat, whatever we are getting, it is in the product. So this reaction is giving me heat rather than taking heat. And here also it represents the same. Okay, so don't go with the sign. Please understand what this sign signifies. Okay, so sign here, it signifies that this heat is given out in the reaction, and here we are just writing it in the product side. So both of them represents the same thing, that heat is given out in the system. Heat is given out of the reaction. Okay, so this is how we write the thermochemical equation. This is how we write the thermochemical equation. Now, we will write many things, that is standard enthalpy. Enthalpy, and there is standard enthalpy. Meaning of standard enthalpy. Okay, standard enthalpy of combustion, standard enthalpy of a particular reaction, standard enthalpy of formation, many things. So the only condition is that it is measured at 1 bar pressure. It is measured only at 1 bar pressure. Second point is that the temperature can be anything. Okay, temperature can be anything, but temperature can be anything but the substance, but all the substance should be in their standard form at that temperature. Okay, at that temperature. For example, what does it mean? For example, I can say I'm using H2O. Okay, I'm using H2O in a particular reaction. So if I'm measuring the standard enthalpy at minus 10 degrees Celsius, then I will use ice. And because at minus 10 H2O should be ice, then I should be using ice at that particular temperature. If I'm measuring at 25 degrees Celsius, then I should be using in that reaction water. Okay, and if I'm having some reaction at 150 degrees Celsius, then I will be using water vapor. Okay, so that is the only case. If you have different temperature, you should keep in mind what is the standard state. Okay, what is the standard state? And if the temperature is not mentioned, then it is 25 degrees Celsius. That is the room temperature. That is the room temperature, or 298 Kelvin. Okay, if we don't mention any particular temperature, then you are going to take it as 298 Kelvin. You're going to take it as 298 Kelvin. So let us first of all write enthalpy of formation. Enthalpy of formation. Enthalpy of formation. What is enthalpy of formation? The enthalpy change. Okay, the delta H when 1 mole of a substance is formed from its elements in their most stable state. In their most stable state. Okay. Now, read this particular line, delta H, when 1 mole of a substance is formed from its elements in their most stable state. Many things are important in this particular sentence, 1 mole. And according to stoichiometry, not according to the reaction condition, 1 mole, that means all of these enthalpies, these are written for chemical reactions. Okay. So all of these enthalpies, they will be written for chemical reaction, not any particular experiment. Please remember that all of these enthalpy of formation of a substance when it is formed from its elements. Okay, from its elements in their most stable state. Most stable state, that means we also have to consider the temperature. And if the temperature is not given, that means we are going to take the temperature as 298 Kelvin. Now let us say I want to form. So all of these enthalpy of formation, whatever enthalpy we are writing, they will correspond to a chemical reaction. So I'm trying to write the chemical reaction which represents the enthalpy of formation of CO2. Okay, so what is the substance that I'm trying to form? Tell me, guys. What is the substance that I'm trying to form? CO2, right? Okay, fine. CO2. Khalil, I can't hear you, by the way. And now you guys tell me, what are the elements that are used in the formation of CO2? CO2 is composed of which elements? Tell me.
Carbon and oxygen.
Carbon and oxygen. Okay. Now, what do you guys think? What is the most stable state of carbon? Most stable state of carbon.
Yes.
Gas. Acha. Have you seen carbon? Is there anyone who has seen carbon, pure carbon? Think. I think you guys, or you maybe, yeah, I think you have seen carbon. I think you have seen carbon. All of you. Think, yeah, you have seen carbon.
Yes, sir.
Tell me, in what form?
In pencils.
What?
Graphite.
Graphite and pencils. है ना? All of you agree? Yes or no? Graphite and pencil?
Yeah, sir.
Right, graphite and pencil.
Yes,
There is
sir.
also one more form that you may or may not have seen. If you have seen, oh my God, diamond. I have never seen diamond, I think. Yeah, but diamond is also completely carbon, correct?
Yes, sir.
Right, carbon and graphite. So obviously, most stable state we will be taking as graphite, Anna, because no one can afford to do reactions with diamond. Okay, so we will use carbon. We will use carbon in this particular reaction. We'll use carbon. Okay, and what is the most stable state of oxygen? The element oxygen. How do you find element oxygen in the nature? How do you find it? What is its molecular
Gaseous state.
formula? Gaseous
Yes.
state as O2, right? As O2, yes or no?
Yes, sir.
Yes, sir.
So this is how you are now. You can see one thing that you have to always keep in mind, that there should be only 1 mole of the product. Okay, 1 mole of the product, no matter what is the stoichiometry of the reactant molecule. No matter what is the stoichiometry of the reaction molecule, there should be only 1 mole of product. 1 mole of product. Okay, so that means that if I write H2 for the formation of HCl, if I'm writing H2 plus Cl2, and if I want to balance it, so I cannot write 2 HCl here. Why? Because I need the products to be 1 mole. So the enthalpy of formation reaction, the way that we represent enthalpy of formations reaction, I will be representing it like this to give 1 mole of HCl. Got it, guys? Yes or no?
Yes, sir.
Yes, sir.
Yes.
Okay. So this is how we represent the enthalpy of formation, and obviously all of these will be with the delta H naught R values. And please just like memorize this value for CO2, minus 393.5 kilojoule per mole. No need to write about HCl and all. Okay. Then you all will tell me, how can I form NH3? Okay. So what will be the stoichiometry of the elements? First of all, tell me, guys, what are the elements? What are the elements?
Nitrogen and hydrogen.
Then you, very good, nitrogen and hydrogen. Now you tell me, how do you find nitrogen in the universe? In what form?
Gaseous.
Gaseous.
What is the formula for nitrogen? Pure nitrogen?
N2.
N2.
N2. Very good, N2 plus, and hydrogen as H2, yes or no?
Yes, sir.
Now you have to balance it in such a way that there should be only 1 mole of NH3. Now you tell me what will be A and B, stoichiometry of nitrogen and stoichiometry of nitrogen. Yes, tell me.
Sir, half NH2.
Okay. And what will be B?
So 1/4 and 3/4.
1/4 and 3/4. No. 1/4 into 2, it will be equal to half. है ना? So here we have N2. That means 2 nitrogen if I take 1/4. So 1/4 into 2, you have the half होगा. Half नहीं होगा ना यहाँ पे. It's not balanced. See, simple. Okay, simple. ये बताइए. How many nitrogens are here? How many nitrogens are here?
One.
One nitrogen.
One.
One nitrogen. So you just write 1 here. Okay. Write 1 here. How many nitrogens are here? 2, na?
Yeah.
So just divide by 2. How many hydrogens are here?
3.
3.
So just write 3. And how many hydrogens are here?
2.
2.
Right. Now you check. Is it balanced? Yes or no?
Yes, sir.
It is balanced. Okay, fine. Now, if you have, next thing is, whenever you write a particular reaction and there is delta H naught R written here, now how will you read this? How will you translate this? You will translate this as, if I make 1 mole of carbon dioxide, if I make 1 mole of carbon dioxide, then 393.5 kilojoule of heat is liberated. Okay. 1 mole of CO2 gives 393 kilojoule of heat. Now you tell me, 2 mole of CO2 will give how much? Tell me guys, 2 into 393.5. है ना?
Yes, sir.
Okay, so this is the information that you are getting. Please don't just leave it as a value. Please understand the value of value. What is this? What does it represent? कहना क्या चाहता है? Delta H naught R is equal to minus 393.5 kilojoule per mole. What does it mean? What is trying to say? What information it is giving me? So if I know for 1 mole, I can calculate for half mole, 2 mole, 3/4, 4/2. So this is why all of the delta H naught R for many reactions, they have been standardized and they have been recorded, so that we know if I start with 5 moles of carbon dioxide, then I should be expecting this many amount of heat, this much amount of heat. Now that is how the petroleum, the fuel industry, it works. This is how the fuel industry works. You have to know the combustion of 1 mole, and then you can say that, okay, fine. If I put, so how you measure the fuel efficiency? Delta H naught R. Fuel efficiency is measured by delta H naught R. How much energy are you giving out if you are burning 1 mole of a particular compound? Okay, fine. So let me tell you. Sorry, Abdul Rahman, you want to say something? Okay, right, next. Calculate the enthalpy of formation from following data. Okay, so what is the data? They have given you a reaction like this. H2 plus Br2, it is giving me 2HBr. It is giving me 2HBr gas. All of these are gases. They are saying that delta H naught of this reaction, it is equal to minus 72.8 kilojoule per mole. Okay, kilojoule per mole. So now the solution. solution. Enthalpy of formation, है ना? Calculate enthalpy of formation. So what does it mean by enthalpy of formation? So delta H naught F, it is represented by delta H naught F. It means is the amount of heat exchange during formation of one mole of HBr. Yes or no, guys? Tell me. This is what delta H naught F will be for HBr, correct?
Yes, sir.
Okay, and what they have given? They have given me the enthalpy of the reaction when we are forming 2 moles of HBr, correct? Yes or no?
Yes,
So I
sir.
will say they have given 2 moles of HBr gives 72.8 kilojoule of heat, right? So 1 mole of HBr gives 72.8 kilojoule divided by 2 mole of heat, right? And hence you can say for HBr delta H naught F, that is formation, it is equal to how much? 36.4, na? Minus 36.4, because it is giving. This gives is represented by this minus sign. Please remember that minus sign represents give. 36.4 kilojoule per mole. So write this reaction. Let me know if you're done. Okay, write this question. No, write this question. Okay. Now in the enthalpy of formation, I just add one more point, that is this is represented as delta H. Okay, delta H. You all wrote the question, yes or no?
Yes.
Okay, fine. Now, right, standard enthalpy of formation. Okay, we will study standard enthalpy of formation. Okay, easy things. Easy thing. What is the standard enthalpy of formation? The delta HF, it is represented as delta HF, and there is a 0 sign that is representing not. Okay, standardized. So delta HF measured at 1 bar pressure. Right, 1 bar pressure. So delta HF naught, the standard enthalpy of formation is AKA, it's also known as standard molar enthalpy of formation. Standard molar enthalpy of formation. Okay. Now, next thing is, if I want to form O2, tell me guys, how will I form O2? What are the elements? What are the elements?
So oxygen.
O2 only, right? O2 only, na? So can you see I'm not doing anything. So by definition, the delta H naught F will be equal to 0. Correct? Because no reaction is happening, right?
Yes.
Okay. So by definition, this is how we have defined a particular standard, how we have defined this enthalpy of formation. And due to that definition, the H naught F, delta H naught formation of elements in their most stable states is 0. It is what? it is 0. What does it mean? It means that the delta H naught F of O2 gas is 0. Delta H naught F of N2 gas is 0. Okay, most stable state. Please remember, most stable state. N2 liquid will have some enthalpy of formation, but gas, no. Delta H naught F of carbon solid, it will be also 0, but not gas. Okay, please remember. Okay, let me write here, but delta H naught F of O2 liquid is not equal to 0 because it is not in its most stable state. The element is not in their most stable state. Okay, now let us write. We have seen two things here. Sometimes we will get delta H naught R, and we have no delta H naught R, that is the enthalpy of standard enthalpy of reaction. It is a generalized term, and then we have specific definition which puts formation. Then we will see combustion. Then we will see some other things also. But enthalpy of reaction is a generalized term, and inside that formation and different specific terms come. We will write the relationship between. You need to understand it more. Relationship between delta H naught R, that is in standard enthalpy of reaction, and the standard enthalpy of formation, Now, let us start like this. If I am going from A to B, I'm going from A to B. Okay, guys, any problem? No problem here. So can I say that I am destroying A and I am forming, then I'm forming B? Yes or no? Tell me, can I say this?
Yes.
Yes, no problem, all of you?
Yes, sir.
No problem now. Okay, fine. Now, if I am destroying A, now you tell me, there's some reaction like this in which A was formed, and the formation of A, it required QA amount of heat. Okay, there was an exchange of heat, it was equal to QA. When we formed A, QA amount of heat was required. Now, can I see when I'm destroying it, then the same amount of heat will be required, but in the opposite direction, minus QA. Yes or no? Because if A was formed and it liberated heat, then I will have to give heat in order to destroy A. Yes or no? Tell me.
Yes, sir.
No problem here, guys. Anyone? Any problem till here? Tell me.
No, sir.
No, no. So when we are destroying something, that means it is opposite of formation. Okay, it is opposite of formation, and this QA. Now, rather than writing QA, and I'm saying it is the opposite of formation. That means when I'm destroying, it is the minus of delta H naught F of A. Yes or no? It is the opposite of the opposite of formation. Now, if I'm destroying something, it is the opposite of formation. That is why I have this is the value of heat exchange when I'm forming it. This is the value of heat exchange when I'm forming it. So if I want to do the opposite thing, then I will just add the minus sign that represents the inverse relationship. Okay, that represents the inverse relationship. And in formation, it is simple. This will be, because we are forming, it will be delta H naught F of B. Any problem, guys? Any problem till here?
No, sir.
No. That means for this reaction, this whole reaction is represented by delta H naught R, and this delta H naught R comprises of this in positive sign, that is delta H naught F of B plus minus of delta H naught F of A, right? And these are the two heat exchanges taking place. When we are destroying A, I need the opposite. I need just the negative sign I just need the opposite of whatever was required when it was formed. Whatever heat exchange was there when A was formed, plus when we are forming B, that means we are just writing delta H naught F of B. And in general, I can write that any delta H naught of reaction, it can be represented as the H naught F of products, H naught F of products minus the delta H naught F of reactants. Yes or no, guys? Tell me, any problem till here?
No, sir.
No, no. Okay. Now you can products. Okay, products. And furthermore, if you want to just error proof this, then you can write the summation sign. That means whatever is the, if you have A, B, C, D, then the enthalpy of formation of product that is from B, C, D minus the sum of the enthalpy of formation of reactants. Okay, enthalpy of formation of the reactants. Okay. Now, this is simple. How you will remember it like this: products minus reactant. Okay, products minus reaction, and in both of them we are using what? Delta H naught F of products minus reactant, and this will be the enthalpy of reaction. So let us write a question. Please write me, calculate the enthalpy change. Calculate the enthalpy change for following reactions. Calculate the enthalpy change for following reactions using given data. So we have 4NH3 gaseous state. You write this question with me, okay? Plus 3O2 in gaseous state is giving me 2 moles of N2 plus 6 moles of H2O. 6 moles of H2O. And you have been given the enthalpy of formation of few things. They have given the substance and enthalpy of formation. Substance is NH3. Enthalpy of formation of NH3 is minus 46 kilojoule per mole. Okay, minus 46 kilojoule per mole. Then we have H2O, and it is minus 286 kilojoule per mole. Okay, so these are the two enthalpy of formation given, and they are asking you to calculate the enthalpy of reaction of this whole enthalpy of reaction. Okay, so write the question down. Let me know if you're done writing the question, then I will ask you a few questions about this question, where you have to see where are you missing something, if you're missing something or not, that those things. Done writing the question, yes or no? Tell me.
Yes, sir. Yes, sir.
All of you done? All of you done?
Yes, sir.
Okay, fine. Now you tell me, if I want to calculate the enthalpy of reaction, then I want the enthalpy of formation of NH3, O2, and also the enthalpy of formation of N2 and H2O. Yes or no, guys?
Yes.
Yes, sir.
Okay, but we needed 4 enthalpy of formation. They have only given me 2. Can you tell me why? Why did they not give me the enthalpy of formation of O2, and why did they not give me the enthalpy of formation of N2? Can you guys think and tell me why?
Because it's 0, sir.
Thank you very much. All of you now remember? Yes, Maimuna, Mazia, Khalil.
Yes, sir.
Why it is 0? Because they are in the most standard states, right? They're in the most stable state. Right, guys? Okay.
Yes.
So when you get this type of question, as any something is missing, है ना? Don't be like this. Okay, fine. Now we don't need O2 and N2. That is for sure. You don't need O2 and N2. Fine. Now you have to also see. Let me write the solution and how this is how you are going to deal with this particular question. So what are we doing now? We are calculating the delta H naught R. Okay, delta H naught R. So this is equal to the enthalpy of formation of products minus the enthalpy of formation of reactants. Okay, fine. So first of all, you tell me in the products, what do we have? N2. So we don't need to write N2, right? I will just write H2O. Now you tell me, is H2O forming or 6 moles of H2O is forming? How many? What is the amount of H2O that is forming according to the reaction?
6 moles of H2O.
6 moles of H2O. Hai na? So we have to consider that also. Because the enthalpy of formation that we have been given, it is for 1 mole, but in this reaction, we are forming 6 moles of water molecules. We are forming 6 moles of water molecules. Then obviously, we have to take in consideration that there are 6 moles of water molecules, and that should also be represented in the formula of delta H naught. So I will write for the products, I will just write let me write it like this only, delta H naught F of N2. So 2 times this, right? Plus 6 times the delta H naught F of H2O minus for reactant we have 4 times the delta H naught of NH3 formation. Again minus, na? Because this will be minus and inside it will be plus, so minus it will be minus. Minus plus will be minus only into 3 into delta H naught formation of O2. So first of all, I will cut these two things to 0 because they are in their most stable state. Then simply we'll write 6 into delta H naught F of water minus 4 into delta H naught F of NH3. Okay, so you just write this. This will be 6 into, write the delta H naught F. This will be 4 into, write that and tell me what is the answer of delta H naught R. Okay, you guys tell me now. No one has problem with these type of, no one will have any confusions, right? With this type of problems, they are easy. Okay, they are easy. I will give you questions in homework so you can practice. We'll do one more question like this.
Sir, why did you put 6 years? Huh?
6 लिख दिया हमने. I'm sorry. Mistake. Okay, Maimuna has calculated. Let us see other answers also, Maimuna. Okay, so Minashi, are you sign देखिए Minashi.
Yes, sir.
Sign is fine. यहाँ पे एक तो N2 या H2O होगा. H2 लिख के छोड़ दिया था हमने. H2O. Look at the sign, Minashi. Six into minus 286, and this will be 4 into minus 46. Mm-hmm. Meenakshi, you are doing mistakes in calculation. What is this value? 6 into 286, Meenakshi, tell me.
Sir,
6 into 2,
1716.
1000,
716.
416, 400, na?
716.
This,
No, 16.
क्या आप थोड़ा सही से बता दीजिए हमको एक बार. हाँ, 1
1716
1716 minus
minus 184.
minus 184, na?
Yes.
And this will be also minus, right?
Yes, sir.
So this will be minus 1716 plus 184.
Minus.
So it will be minus 1532, na?
Yes, sir.
Kilojoule per mole. Your first answer was right. I was just telling you to check the sign. है ना? Telling you to check the sign. Done, all of you? Yes or no? Tell me.
Yes, sir.
Yes, sir.
Okay.
Yes.
Done? No.
Yes, done.
Done. Okay, fine. Now see. We have seen a simple reaction, simple question. है ना? इसमें क्या था? इसमें you were given the F naught of products, F naught of reactants, and the delta H naught R was asked. But you know that you can be given the delta H naught for the reaction, enthalpy of reaction. Some of the enthalpy of products will be given, some of the enthalpy of reactions they will be given. And if there is one unknown in the enthalpy of formation of reactants or products, that can also be asked, right? That can also be asked. So we'll look at that type of question. Now, please write. So in the previous case, enthalpy of reaction was asked. In this case, you will be asked about one of the formation, enthalpy of formation of either a product or the reactant. So write the combustion of benzene. The combustion of, wait a second, 1 mole of benzene. Mole of benzene. One mole of benzene gives 1 mole of benzene gives CO2 and H2O with 3267 kilojoule of heat. Kilojoule of heat at 298 Kelvin and 1 bar pressure. And 1 bar pressure. Okay, 1 bar pressure. They have given you some values. Calculate the delta H naught F of benzene. Delta H naught F of benzene if the enthalpy of formation of CO2 it is equal to 393.5 minus 393.5 kilojoule per mole, comma, enthalpy of formation of H2O is equal to minus 286 kilojoule per mole. Okay, so write this question. Let me know if you're done. Done, guys. Write this question. Let me know if you're done. Done. Marcia is done. Okay, waiting for others.
Done, sir.
Done. Okay. Now, in this question, the most important part, the most important thing is this information that combustion of 1 mole of benzene. Okay, so we need to write the reaction. We need to write the reaction in that terms that we have only 1 mole of benzene in the reactant. Okay, so we are, because we are having combustion, and this value here now, that is 32.67 kilojule. It is given for 1 mole of benzene. So let me write the reaction. Okay, let me write the reaction. Just listen right now. We have C6H6 plus O2 is going to give me carbon dioxide plus H2, है ना? Because benzene has only 2 things, carbon. So carbon will react with oxygen to give carbon dioxide. Hydrogen will react to give H2O. And so let me just write it like this right now. Okay, now let me just start to balance this. So you will see that 6 of CO2 and hydrogen is how much? So 3 moles of H2O, and how much O2 will be there? Okay, fine. Let me do one thing. You just balance this, okay? You just balance this. I'm giving you 2 minutes of time. Try to balance this reaction. Tell me. किसी का आया आंसर for balancing?
Yes, sir.
Tell me, Khalid. How many benzene molecules? Yes, tell me. How many
1.
benzene molecules? 1. Okay. How many O2?
15/2.
15 by 2. Okay. And there will be 6 and 3, right? Yes or no?
Yes,
Yes.
sir.
Hannah, all of you got the same thing?
Yes, sir.
Okay, fine. Hannah. So for this reaction, I can write that delta H naught R is equal to 3267 kilojoules. Yes or no? Correct, guys?
Yes, sir.
Okay. Now let us suppose if I said 2C6H6 plus 15 O2 giving 12 CO2 plus 6 H2O. Can I write that delta H naught R is equal to, sorry, this will be minus 32 because it gives, will be equal to minus 3267 kilojoule. Can I write for this reaction?
No, sir.
Why not?
Sir, because the values are different.
Because this reaction is, they are saying that if 1 mole of benzene is if the 1 mole of benzene, if we are having a combustion of 1 mole of benzene, then this much amount of heat is released. Now in this reaction, we are burning how much? We are burning 2 moles of benzene. So obviously this will be doubled. Okay, so this value should not be true. So So this is how you write the chemical reaction. It affects the enthalpy of reactions also. Okay, for now it is fine that delta H naught R I can write here is delta H naught R, it is equal to minus 3267 kilojoule. And why did I write minus? Because here we have the word that is gives. We can write delta H naught of formation, it is equal to delta H naught F of products minus delta H naught F of the reactants, right? Of the reactants. And furthermore, we can write that delta H naught F of products, right? In products, what do we have? CO2 and H2O. How many CO2? 6H CO2. So I'll write 6 into delta H naught F CO2 plus 3 into delta H naught F of H2O minus, in the reactants we have C6H6 and O2. So for O2 we don't need to write, yes or no? For O2, wait a second, this will be delta H naught R, my bad. Do I need to write the formation of O2? Yes or no? Tell me. Enthalpy of formation of O2, it will be 0 only, na? So
Yes.
delta H naught F of C6H6 minus delta H naught F, this will be 15 by 2 of O2. But however, this complete thing will be equal to 0 because O2 is in its most standard state. So H naught R is minus 3267, right? Minus 3267. And I need to find H naught F of benzene. So I will take this benzene towards this side of the equation and take this value towards this side of the equation. Okay, so minus delta H naught F will become the plus delta H naught F of C6H6. This will be equal to 6 times for CO2. It is how much? 393, na? 393.5 is me and 0.5 plus 3 into delta H2 is 286, right? Minus this also will be minus 286 kilojoules per mole, minus 286, and here we'll be having plus 3267. All these value will be in kilojoules. So calculate this and tell me what is the answer. I got the answer. Memuna ne bajwa diya. Correct, Memuna, correct. Yes, Khalil and Minashi, correct. Anyone else did not get the answer? What about Muhammad? Sayyid Muhammad, Abdul Rahman, Razan, Mehreen, guys, what happened? Calculate and tell me what is the answer.
Sir, where did you get this 2 minus 286, sir?
तो है ना सवाल में. It's not type of water,
Oh, okay, sir. Okay.
है ना. This portion, when we apply thermodynamics to chemistry, it is known as thermochemistry, and it is mostly, what I will say is that it is arithmetic and some stoichiometry, chemical reaction chapter first. The chapter first we studied stoichiometry now. So it is combination of these two things: a simple arithmetics, a linear equation in one variable, because we have only simple reactions here, simple equations here. Yes, Abdul Rahman, correct. है ना? This will be 48 kilojoule. है ना? On those people who are not solving this simple questions, I have done all the work, right? You just need to calculate these things. Please don't get lazy at this time. Okay. Calculation, you cannot run away from calculations. 48 kilojoule will be the enthalpy of formation. And since it is 1 mole, you can also write 48 kilojoule per mole. Okay. 48 kilojoule per mole. Now see the beauty of these enthalpy of reaction and the relationship that we have got. Enthalpy of a reaction, it is equal to the enthalpy of formation of products minus the enthalpy of formation of the reactants. So the beauty is that if I know the enthalpy of formation of carbon dioxide and water, then I can calculate the enthalpy of formation of not only benzene but any other hydrocarbon. So because as you can see, if I will have an alkane, it will be CnH2n plus 2 plus O2, and it is going to give me what? Carbon dioxide plus H2O only, right? Now I can balance this reaction. Okay, I can balance this reaction, and if I know the enthalpy of this reaction, then I can calculate the enthalpy of formation of the alkane also. Okay, and as you can see, what we are doing, we are burning, and if we are burning, then we can calculate the delta U in the bomb calorimeter. If I'm calculating the delta U, I can calculate the delta H also. I can calculate the delta H of this whole reaction by the relationship that delta H is equal to delta U plus delta NGRT. Okay, so all of this combined, this led to a huge repository of data of different enthalpy of formation, which is used in almost all of the industries now. So these simple relationships are very important. These simple relationships, enthalpy of formation is equal to enthalpy of reaction is equal to formation of products minus formation of reactants. Okay, further moving on. Now let us say enthalpy of formation of C6H6. We have done that, and we calculated the enthalpy of formation by reacting it with oxygen and by the enthalpy of formation of carbon dioxide and H2O, and the enthalpy of reaction of burning the benzene. So in this case, what you can see, this reaction enthalpy of formation of C6H6, it is equal to enthalpy of formation of CO2 plus the enthalpy of formation of water minus the enthalpy of enthalpy of formation of CO2, enthalpy of formation of H2O, and the enthalpy of, this is the combustion, enthalpy of combustion of benzene. The enthalpy of combustion of benzene. Now, if you look at this reaction, then see, to calculate the enthalpy of formation, what I did 6 into the enthalpy of formation of CO2 plus 3 into enthalpy of formation of H2O plus, here we had 3 to 6, 7. This is the enthalpy of combustion of C6H6. Yes or no? This was the equation, correct? Guys, tell me. And we
Yes.
found the delta H0F of carbon, oh sorry, benzene, C6H6. Now, we all know whenever we write enthalpy of formation of something, enthalpy of formation of CO2, enthalpy of formation of H2O, this will be minus sign, no? What was it, minus or plus? Yeah, okay, it was plus. Okay, now, whenever we write enthalpy of formation of CO2 or enthalpy of formation of water or the combustion of benzene, they all represent some reaction, particular reaction. Yes or no? Yes or no, guys, tell me. They all represent enthalpy of some reaction.
Yes.
Yes,
They
sir.
all. Now, this reaction, that is carbon plus H2, will give me C6H6, and we can balance this reaction, carbon, 6 carbon atoms, and you will have 3H2. It is going to give me benzene. This reaction you can write formation of will be carbon plus O2 is giving me CO2. Okay, for H2O you can write H2 plus O2 or half O2. H2 plus half O2 is giving me H2O, and this is the reaction that they have given in the question. This is the reaction they have given in the question. So if you arrange these, all of them, if you arrange all of them and you add this reaction plus the reaction that they have given in question, it will give you this reaction. Okay, it will give you this reaction. And this concept of adding different reaction, it means that if I can calculate the enthalpy of reaction direct from this reaction also, or by summing up all these reactions, it means if I go from A to B, then to C, then to D, right? And in this I put in 100 joule of energy. And here from B to C, I liberated 200 joule of energy. And by going from C to D, I again inserted, let us say, 50 joules of energy. Okay, 50 joules of energy. But I can also go from A to D via a different path. And via a different path, here I am making X, and X is giving me D. So it doesn't matter whether I go from this path or this path. Through X or B, C, D, the energy change from A to D will be the same. The energy change from A to D will be the same only. It will not depend on what path I am choosing. What path I am choosing, it will only depend on the initial and the final product that we have. Only the initial product or the final product. As you can see here, whether we start from these things or we derive the enthalpy of formation from different reactions, the answer it is going to be same. The answer is going to be same here. Okay, so this concept of summing up different reaction in order to get the enthalpy of formation or the enthalpy of reaction, it is known as the Hess law of constant heat summation. So what I'm trying to say, if I want to go, for example, let us directly from A to D, then the amount of energy that I will be, the exchange of heat that will be taking place will be equal to 100 plus 100 minus 200 minus 100 and plus 50. So minus 50 joules of energy will be required. Okay. Now, if you go even from this part, so you give in 100 joule of energy and you give out 200, that means you have minus 100. Then you again put in 50, that means minus 50. So whether you go from whether you have multiple step or a single step, the heat exchange between system and surrounding will be always equal. And this is the concept of heat of rather Hess law of, right? Hess's law of constant heat summation. Constant heat summation. So in this, it says that it simply says that if reaction takes place in several steps or single step, the delta H naught of reaction is the sum of the delta H naught of reaction of intermediate reactions at the same temperature. Okay, so please write, if a reaction, you don't write, just listen. If a reaction happens in several steps, then the H naught R, that means enthalpy of the reaction, standard enthalpy of reaction, is the sum of enthalpy of reactions of the intermediate steps. Intermediate steps. That's it. And it also means that it doesn't matter whether we calculate the enthalpy change for a particular reaction, if it is done in single step or if we calculate it in multiple steps, the enthalpy change will be same. It says that the enthalpy change delta H for a reaction will be same independent of the path. It doesn't matter whether we are doing that in single step, that is whether it is done in single step or multiple steps. Okay. So after this, I just want you, fine. You just write till here, then we'll look at Hess law of, no, not right here. Let me just share you this PDF. Hess law of constant